Okay. So I'd like to welcome you all to another edition of Quantum Fluids and Isolation. So today we have Professor Subir Sachdev speaking. Now, Sachdev is probably a person who doesn't need any introduction, but I think I'll attempt to anyway. So Professor Sachdev got his Bachelor of Science in Physics from MIT in 1982, his MA in Physics from Harvard in 1984, and his PhD in Physics also from Harvard in 1985. He was a postdoc at AT&T Bell Labs from 1985 to 1987. He was then professor at Yale from 1987 to 2005, and then professor at Harvard from 2005 to present. He was also the Energy James Clerk Maxwell Chair in Theoretical Physics at the Perimeter Institute from 2014 to 2019. He was chair of the Harvard Physics Department from 2018 to June 2020. And at the moment, he's a Herschel Smith Professor of Physics at Harvard from July 2015 to present. He's a recipient of many awards, including but not limited to the Sloan Foundation Fellow 1989, a Fellow at APS 2001. He was elected to the US Academy of Sciences in 2014. He won a Dirac Medal from the Australian Institute of Physics in 2015, the Lars-Onsager Prize in 2018, the Dirac Medal from the International Center for Theoretical Physics at East Italy in 2018, along with Dan Thomson and Jacques Nguyen. And he is a member of the American Academy of Arts and Sciences in 2019. He's the author of two books, the Quantum Phases Transitions book, now in its second edition, and he is co-author with Andrew Lucas and Sean Hartnell on holographic quantum matter. And today he'll be talking about novel approaches to matter without quasiparticles. So please help me in welcoming either by unmuting yourselves and clapping or by clapping virtually, Professor Subir Sachdev.
Okay, well, thank you very much, Joshua, for that most complete introduction, and also for having live copies of both my books. I appreciate that very much. And thanks for organizing this great seminar series. All right, so I got to do some sharing now. And oops, what happened? Oh, yeah, sharing the whole screen. And okay, do you see my, is it looking good now?
Yeah, it looks good.
Looks good.
Oh gosh, I've lost my, 1 second. I've lost my mouse. 1 second. Oh, sorry, I shouldn't have just, oh, there we go. Okay, share again. All right, now you all see the green circle, I hope.
Yeah, looks good.
All right, so I'm going to talk about some actually fairly recent work with a number of people. So let me first give all credit to my many collaborators. I'm going to summarize the results of several different collaborations. So it all started with this collaboration with Antoine George Flatiron, and work with Darshan Joshi, Chen-Yuan Lee, and Grisha Tanapolsky on we're looking at a random TJ model. I won't really go into the details of what's in this paper, though. I'll try and focus on some more recent work. Then I have to mention this paper with Hayu Guo and Yingfei Gu on transport in some of the models from last year, well, written last year. And the main part of the talk will be about work that's just about finished with Maria Tiganovskaya, Grisha, and Hayu. And there's some forthcoming numerical work with Henry Shackleton and Alexander Vitek and Antoine. All right, so that's a appropriate acknowledgement to many people who are involved in the results that I'll present. So the work is broadly motivated by the cuprates, but I wouldn't go as far as suggesting I'm going to fit any data in the cuprates. And just a quick reminder of the phase diagram of the cuprates as a function of temperature and hole density. There's a regime at high density called the Fermi liquid, which behaves in a conventional way. There's a pseudogap metal, which has all kinds of anomalous properties that I will not review for sake of time. But other than mention this very nice recent experiment, which will be in a sense related to the models I'll study, which shows that at low enough temperatures and high enough fields, there is some kind of spin glass order below the pseudo gap. So there's some quasi-static spins, which are obviously playing some role in the physics of the pseudo gap. What happened? Okay, so the other portion of the phase diagram I want to mention is the strange metal that appears somewhere between the pseudo gap and the Fermi liquid. And the property of the strange metal is that the resistivity is a linear function of temperature. And which is highly anomalous. Now, getting something linear in temperature at high temperature is not that surprising. It can be understood in many different ways, but getting it down to extremely low temperatures of just a few Kelvin is, largely a mystery. Moreover, if you just assume a Drude-like formula, which you really have no right to, but if you assume one and then convert the resistivity to a time, let's call it the Drude time, then to a remarkable consistency in variety of materials, you find that this time is basically the temperature in units of frequency. And this number alpha is, within a factor of 2, unity in variety of materials. So, you can question the details of this and exactly how you went from resistivity to time. But it's clear that there's something mysterious here at very low temperatures. Okay, so you could say that a challenge for theory is to come up with a model of a metal, which for some somewhat generic reason has a resistivity that goes linearly with temperature as T goes to 0. So it'd be good to, in my view, good to have a theoretical model, no matter how artificial, for which this is true. And I'll tell you about our work on this question. And okay, there's still some issues with it, but I think we have there's some hope that we may be close to such a model. Anyway, okay. So the basic models I've described today are kind of artificial in the sense that they have random couplings in which all sites are coupled to all other sites. I mean, that's I think a reasonable starting point to talk about some kind of mean field theory of a system. So that's really the way it should be treated. And as to the question why such a mean field theory will actually apply to a real system, that's a very difficult question that I will have little to say about. But let me give you some motivation. Why would you want to study such a system? First of all, the systems are indeed random, as you can see from the appearance of spin glass order that I just showed you. Furthermore, the models we'll study, although there's randomness, it's all self-averages. That is, you have a bunch of sites with all kinds of random couplings, but each site is coupled to so many other sites that every site is essentially identical. So even in one sample, provided it's big enough, and if you really did this on a computer, and for some of the models I described, this has been done, you will find that every site looks the same to you if you just measure local correlation function. So it's as if the randomness is not there. At least, you'd have to work very hard to see that the couplings are not random, which are self-averages. Okay. Yeah, so and then this transition or whatever that's happening in the cuprates, it's clear it's not associated with any symmetry, any particular translational symmetry doesn't seem to be that crucial. So whatever theory you come up with shouldn't really use these symmetries. So why not just get rid of them and make everything random so those symmetries are not there to distract you. Okay, yeah, so this is something I've already just said. And finally, the other reason for studying it, in the end, all of these problems map onto a single a quantum impurity problem. Now, of course, there's a long history of people studying quantum impurity problems, the Kondo problem and the multi-channel Kondo problem and all its cousins. But those problems typically have one spin on a few degrees, local degrees of freedom, which we call the impurity coupled to an environment, the bulk, which is known. The bulk is something is simple. It's either a Fermi liquid or a Luttinger liquid or something, or even a conformal field theory, but it's an actual bulk which has its independent existence. Now, when you take problems of the type I'll describe today, the bulk doesn't have an independent existence. The bulk obeys a self-consistency requirement that it should be the final answer for the bulk should be the same answer that you get on the impurity. Okay, so that's the flavor of what's called dynamical mean field theory or extended dynamical mean field theory. And the equations we get are closely related to some non-random dynamical mean field theories, which are generally uncontrolled, but become better and better in higher dimensions. So, and these models have no randomness at all. So we do believe that the physics I'll describe has some connection to models without randomness, but it's good to be safe and work with the actual model. So what we prefer to do is to solve a known model as best as we can, solve an approximate model as best as we can, rather than solve the real model in an approximation that you know nothing about. I mean, the two in the end lead to similar answers, but I think greater insight from the first approach. Okay, so those are all the motivations for, and finally, of course, these models are simple enough that you can make a lot of progress and even compare your wild ideas with actual numerics. Okay, so I'll begin with the heart of the story, which actually is the random J model, which is the model that I introduced with Ye in 1992-93, and update you on everything we know about it today. Okay, so this is the basic model. We have a bunch of spins on n sides with random interactions Jij. So Jij is just Gaussian random numbers with zero mean. Okay, so there's Jij between any pair. So here I've written it out explicitly. Jij's are random numbers with zero mean. And I choose to write it out in terms of these fractionalized particles, these spin-ons on each side, which obey the constraint that f dagger f equals 1. All right, so we'd love to solve this problem. But this problem, even as stated, is too difficult. But we can do now, fairly complete numerics, and I'll show you the results of the numerics, and also solve an extended version of this problem. So the problem we're actually going to solve, whoops, I don't know why this keeps happening, is to take this constraint here, take this constraint, f dagger f equals 1, and alpha going over 2 values, and extend the values of alpha instead of going over 2 values to go over m values. So now I have another parameter, m. Here, n is a number of sides, and which will always be taken to infinity. But m is finite in the actual system that we're interested for, but we're also going to send m to be large, but not as large as n. N is first sent to infinity, then followed by larger. Okay, so now I have defined the problem for you completely. You just put the constraint, this is equal to m over 2, alpha takes m values, and then ask what's going on. All right, so when you take this model, take the large and large m limit, everything reduces to the solution of these two equations. So G is the Green's function of the f, these spin-ons, I'll call them from now on. So this is just Dyson's equation. And the net content of everything is sigma equals j squared, is this equation right here. So really for the next 15, 20 minutes, I'm just going to be telling you about the solution of these two equations. It's nothing more or no less than that. Well, okay, there's certain analyticity properties that we naturally impose on any unitary field theory. So those, of course, have to be imposed, and we have to find the solution of these two equations. So this might, if you when we first heard on this equation, I said, oh yeah, this should be easy. We're still learning more things about the solution of these equations, including the stuff that I'll describe to you. And these equations have inside it, as I'll show, and something associated with the quantum gravity. It's going to have a graviton mode that's going to determine the spectrum of the solution of these very innocuous looking equations. All right, the first thing you can do is just solve it at long time. So you take zero temperature and you take times much bigger than 1 over j. This is we already did. Then you can solve it, and I won't go through the steps. It's a fairly standard asymptotic analysis of these two equations and taking some Fourier transforms. You end up with the result that the Green's function goes as 1 over square root of time, and the spin-spin correlation function goes as 1 over time. Okay. All right, so now we want to go beyond this leading asymptotic result, and we also want to understand what happens at finite temperature. Okay. So for this, it was some of this was understood before Kitaev, but Kitaev really presented in a way that the solution becomes very clear. So what you notice here is that the self-energy goes as square root of omega. So if you compare the self-energy term with the basic, the free term here, as omega goes to 0, this is much larger than that. So let's just look at that problem in the limit where we ignore that term. So there's going to be corrections due to this term that we will very much be interested in, but for now, let's ignore it. So if you ignore this, then this Dyson's equation, it's good to write everything in 2 times. Dyson equation just becomes this integral equation in time. And this equation becomes this here. I'm now just separating the times. And these equations can be solved completely, both at 0 temperature and finite temperature. And they also have a huge amount of symmetry. So I'll present to you the modern way, due to Kitaev, how we understand the structure of these 2 equations. So the most important property of these equations, which are written here again, to remind you, is that they're invariant under both a gauge symmetry and a time reparameterization. So if you take tau and write it as some other monotonic function of some other variable sigma. So tau, if you had finite temperature, tau runs from the circle, is a periodic time on the circle. Sigma is also a periodic time on the circle, and there's just some map, monotonic map from one circle to the other. It is some continuous monotonic map, f of sigma. Okay, so if you now take a new time tau, and then you define a new function g tilde at the new time tau, which is related to the old function, but then you put in these factors, which involve the derivatives of this transformation to some powers. Ignore the little g's for now. Then it just takes a few lines to see that the new equations for g tilde of little sigma will be exactly this form. They'll have exactly this form with no change, except you replace tau by sigma and g by g tilde. So that's the time reparameterization symmetry. And in fact, this is kind of easy to see. And the whole point of this is that there is in these equations, no other degree of freedom which has some prescribed time dependence. The time dependence is coming on its own from the self-consistency. So this kind of symmetry is, for example, not present in the multi-channel Kondo problem. They only have some boundary conformal symmetry. This is a much larger symmetry. And the reason is the multi-channel Kondo problems, even though ultimately there's a very beautiful conformal field theory for it, you're interacting with a bulk which has a prescribed time evolution. There's no prescribed time evolution here. And that's really the key to everything I'm going to talk about. Okay, so that's one important thing. The other one is like a U1 gauge transformation, which you can also much more easily check. It's important for some things which I really won't have time to discuss. Okay, so the first thing you can do is imagine that one of the solutions at 0 temperature, where temperature goes to infinity, 0, sorry, and then do this map, use this conformal map to map the line to a circle, and then you'll find that you get the finite temperature correlation function. Now, you might think there's other choices for this map, but this map has a unique property that if the Green's function we're interested in only depend on the differences of the two times. And as you can see here, if I pick some arbitrary time reparameterization, even if G was a function of the diff of tau 1 minus tau 2, there's no guarantee that G tilde is a function of sigma 1 minus sigma 2. So and this is one of those functions for which that works out. Okay, so yeah, so I guess I've already sort of showed this. It's in general, G tilde is not a function of sigma minus sigma 2. So when we take a saddle point, so it seems like you have an infinite set of, if you give me a solution to these equations, by doing a time reparameterization, I can give you some other solution. So it seems like I have a huge number of saddle points to worry about, and the whole problem seems ill-defined. But if you add the constraint that things only be function of time differences, then actually it's a much more limited symmetry. So the time reparameterization symmetry is spontaneously broken by the physical set of saddle points that you have to choose. This is in the approximation that the I omega term is not there. So then you can ask the question, suppose I only look for transformations which preserve the fact that the Green's function is a function of sigma 1 minus sigma 2, and also equal to, have this power law structure in my preferred time frame. Okay, so if you do that, sorry, I have these pictures of everybody that are messing the screen up. You find that there's a preferred time reparameterization under which G goes back to itself. G becomes equal to G tilde, has the same form, has this exactly the saddle point form. And that's and these are these rational transformations. This is in the line. You have to generalize this to a circle. I haven't written that down. And so these are from the group SL2R, which is just a group of simple linear transformations of 2 by 2 matrices with determinant 1. The S tells you that it's a determinant 1. Okay, so what we have is in the limit you drop the I omega term and exact time reparameterization symmetry, but it's only approximate because of the I omega term. And this is spontaneously broken down, if it's exact, down to SL2R. So it's somewhat analogous, to a ferromagnet, which in a tiny little field, ferromagnet where the field is an irrelevant operator. An actual ferromagnet, the field is not an irrelevant operator. So the field tells you to point in some direction, say the North Pole, and then you have the only symmetry you have is rotations about the North Pole, and that's the analog of the SL2R symmetry. Okay. So once you understand the structure of these symmetries, many things follow. So in particular, like I said, you can take the 0 temperature solution and map it to finite temperature, and you get these forms that were known to Georges and Parcolet. And if you now take the spin-spin correlation and compute the local susceptibility, which quantity you measure in neutron scattering experiments, it has this tanh omega over 2t form, which is the kind of form that people interested in things called marginal Fermi liquids are very interested in. And in fact, that was something I already recognized in the paper with Ye, that these susceptibilities have this so-called marginal form, and it just drops out from the problem. It's not something you put in by hand. Okay. All right, so now the question is, this is really the topic of all the recent work, can you go beyond this conformal answer? What can you say are the corrections to this at low temperatures? And that turns out, as we'll see, to be crucial to understanding the resistivity of these class of models. So what we're going to do is we imagine we are in some low energy limit at some conformal fixed point with this. Here, CFT refers to the SL2R symmetry, which is the conformal group in 0 plus 1 dimensions, if we just analytically continue it from higher dimensions. Okay, so this is going to be perturbed by this operator in the UV. But in the low energy limit, what will happen, like in any fixed point, you're going to generate all the possible irrelevant operators. So you just take this particular operator in the low energy limit, we write it as the sum of some eigen operators which have or the primary operators as they call, which have some scaling dimension h. So all of these terms are allowed. And in principle, then, if you are doing what's called conformal perturbation theory, all you need is the values of this G sub h. That's not something that's very easy to determine. You'd have to do some numerics, and we have done some numerics to determine what the numbers are. But once you know these numbers, in principle, you have some asymptotic low frequency expansion for the Green's function. In particular, fairly standard scaling arguments. So if this OH is an operator which decays as tau to the minus 2h, so h is its scaling dimension, then just by some simple scaling argument, you can see that the correction to the conformal Green's function should be of this form. And there's a sum on h here. You can take all of these terms and give this leading corrections with some coefficient alpha sub h. And this coefficient alpha sub h can be related to G sub h by just doing perturbation theory expansion, and you can see this related to some 3-point correlators of this O sub h. So if you want to understand these terms, I mean, it becomes a question of asking, what is h? What are the values of h? This is called the spectrum of the conformal field theory. What are the values of h? And now, if you take, usual two-dimensional conformal field theory with c less than 1, those have, those are called, obey this Virasoro algebra, and they have, for c less than 1, only a small set of allowed representations, and they all have some primary fields which are finite. There's a finite number of primary fields which have all rational values. This is, of course, the famous result of Zamolodchikov, Polyakov, and who's the other one, Knizhnik, and also by Friedan and Schenker. Okay, so that's in 1+1 dimensions. Now these models in 0+1 dimension turn out to be more complicated. They're not like the C less than 1 conformal field theory, which are much simpler. And those C less than 1 conformal field theories are very similar to the multi-channel Kondo type fixed points. This is quite a different beast. In particular, it will have irrational scaling dimensions, an infinite number of primary operators. So it's much more strongly coupled. And it's all due to this self-consistency requirement. So how do you determine the values of H? Well, this is the simplest way to understand it from a condensed matter point of view. You just try to compute the 3-point correlation function of your operator, which is, say, this operator, F dagger F, with some derivatives, with 2 fermions here. And in the large N limit, you can see that you can rewrite this as this kind of equation. You just have to sum all the bubble things. So now you take this this graphical equation and you look for a solution where this is purely power law and the bare term vanishes at long distances. This is the singular term is more important than the bare term. And when you do that, and this really it's a 2 or 3 line calculation. I mean, not 2. It's about a page or 2 of some complicated integrals, and that from that you can figure out what the values of H are. And it's useful to divide the H into 2 towers, 2 infinite towers, ones with odd number of derivatives of the A tower and the S tower, and the values of H, of the scaling dimensions of these operators, which determine all those corrections, are just given by the equation K sub H equals 1, K sub H equals 1, where these are the functions. Okay. All right. So these have been obtained by various people from many different methods. I'm showing you the method that I've seen, which is really the simplest for me to understand, by Klebanov and Tarnopolsky and their collaborators. Okay. So if you look at these equations, they do have an infinite number of solutions, which are irrational, but there are 2 solutions that are rational, and in fact integer. And one of them is H equals 2, because you can just check if you put H equals 2 here, it's equal to 1. And what is that mode? Well, that operator is precisely the time reparameterization mode. So there's a protected mode from time reparameterization symmetry. This is very much analogous to ordinary conformal field theory, where you associate with, you have the stress energy tensor and you have the currents, and their scaling dimensions are protected. because they're related to conserved quantities. The integrals are conserved quantities. So here, this is the analog of the stress energy tensor. It's this time reparameterization mode, and its scaling dimension is 2. And then the other one is, of course, the conserved current, which in this case is an emergent U1 gauge symmetry, and its scaling dimension is 1. Okay, so that's a lot of technicality, but I think I'm almost done with the technicality, and we'll be showing you some results now. Okay, so and what we have done in this paper is generalize this away from particle hole symmetric case. And anyway, just so for now, let's just focus on the particle hole symmetric values, and you can see this is the 1 and this is the 2, and then these are the other ones that appear. You can get this, of course. There's an infinite tower of these irrational numbers. This is the gauge mode, this is the time reparameterization mode, which are very robust and don't depend on anything. And all others depend on everything else and some bizarre set of numbers. All right, so now we know the values of H, and not just for this model, for many other models, and I'll spare you the details. Okay, so from this, we can now do the series. Okay, so like I said earlier, I should have put a sum over H over here, and we can literally find many of these terms. And in fact, we can also compute, and that will be in the paper to appear, terms that depend on the square of this. There's also a term at second order, which depends on alpha H squared, and so on and so forth. Those also you have to worry about. So the leading terms for the simplest SYK model give you this. So this is the series that we've generated from these methods. And the first term, okay, so the most important terms are, of course, come from the lowest modes. So this is the gauge mode, which has dimension 1. And as you can see from here, the correction goes as power H minus 1. So that just gives you a constant. And in fact, that mode is ultimately related to a Luttinger theorem. And you can relate it to an overall prefactor in front of the Green's function and some spectral asymmetry. So I won't go into that. So the H equals 1 mode is fully understood, and we don't have to worry about it. So then what's the next mode? The next mode is H equals 2, and that'll give you a 1 over tau correction. And in frequency space, that gives you a correction, which is omega over J. Okay, with some coefficient here. And this coefficient then is related to the strength of the time reparameterization mode. And the next term turns out to be, before you go to any other operator, the square of that, and we can get this coefficient. And this is the new operator, 2.77 is 3.77 minus 1. And my collaborators are really amazing. They went all the way up to here, omega cubed. So there's only 2 free parameters here, alpha 0 and alpha 1. And this is now a comparison of the solution of the SY equations with this kind of expansion and at 0 temperature, and it just works remarkably beautifully. You can, from this kind of, so this is, you're plotting here G of omega, which is square root of omega times G of omega. So there's a divergence at square root of omega at small omega that we've taken out, and we're looking at all the corrections to that. And now this alpha 0 actually had been computed earlier by Maldacena and Stanford, and they related it to the specific heat. So this model has a specific heat, which is linear in temperature, so it has a Sommerfeld coefficient. And this alpha 0 can also determine the Sommerfeld coefficient. And it agrees beautifully from the fits to the spectral function. All right, so I have lots of data like this, which really quite amazing how well it works. This is what happens when you have spectral asymmetry. Then the functions are different for particle-like and hole-like excitations. And here we can take the first 2 terms and even look at the ratio of the corrections for both positive and negative frequencies are determined by the same operator. So there's no free parameter. Once you fit the positive, you have to fit the negative with the same parameter. So that also works extremely well. This is some other particle hole asymmetry, more complicated functions. And this is the ratio. Like I said, you take the ratio of the correction of particle-like and hole-like excitations, and this is what you get from the numerics and compared to the predictions from this conformal perturbation theory answer. All right, so that's, no surprise, but it's really amazing that Maria and Grisha and how you were able to take both the numerical and the analytic analysis so far that really check the nitty-gritty details. Okay, so now for something. Yes.
Yeah. Hi, Subir. How are you doing? I'm enjoying this. Just a simple question. I would have an expectation, right, that when you get really in the UV, that you get sort of messy stuff. How is it? Is this expansion? Is it going on all the way to the deep UV problem? How does that work?
Yeah, well, it's an asymptotic expansion from this point.
Yeah, I understand, right? But how far do you get up?
So what we believe at the UV, and there's some paper by Ahud Altman and collaborators on that. In the UV, it's e to the minus omega. It's an exponential decay. That's given by some arguments based on moment expansions. So that's totally UV behavior, and so at some point it will cross over to that exponential behavior. But we're just expanding about this point here.
So the IR expansion, right, you cannot really get through the crossover to that UV part, I guess.
No, not really. Yeah, you can try to make it better and better down here. Yeah. But the the UV in principle, for example, if I took a slightly different model, so I have a spin-dot-spin interaction. Suppose I put in a 4-spin interaction or a 6-spin interaction. That will change the UV completely, but it won't change this expansion. It'll only change the values of these numbers, alpha 0, alpha 1, and so on. Okay. Perhaps, all right, so I was showing.
Just curiosity, right? Is there a radius of convergence of the expansion?
It's not, it's probably 0. It's an asymptotic expansion.
Yeah, real asymptotic. Okay. Good.
Yeah. Okay, so you can now you can do all of that at finite temperature. That's very tricky. They've only worked it out to the first non-trivial term. So for example, the local spin susceptibility, which initially was just a tanh, and now after a lot of work, we get this correction. And here there's no free parameter. You can actually fix the correction to the specific heat value. So, okay. And if you at 0 temperature, we can get many more terms, but finite temperature, generally, things that get much more complicated out there. Although in principle, they are computable. All right, so this is then our correction to the famous tanh. So here, just for fun, I've plotted this tanh, this function for some small value of c. And without making any claims, it's just I was excited to see that if you looked at some old data on people measuring local spin susceptibilities of random magnets in the cuprates, there's quite a few papers, and there's also papers in heavy fermions and strongly interacting random systems and some kind of magnetic or Kondo transition. You get local susceptibilities that have this generic form quite well. All right, I don't know. I think it'd be worth investigating, but anyway. But I think I think this is a good starting point for understanding systems of this type. Okay, so the next thing I want to show you is comparison with exactly the model I started with, but which is now studied in numerical diagonalization. So that is this model here. We go back, so just to remind you, so that was a lot of technicality, but now it's just going to be a presentation of various results. So this model for SU2, we can just put on a computer and exactly diagonalize it. And then you average over various GIJ. And so that's one of the nice things about randomness here is that, because you can average over so many samples, you effectively get a faster approach to the thermodynamic limit. There's no special features of a given sample that kind of make things oscillate. It just smoothly goes to infinity once you average over many samples. Okay, so yeah, so you compare the results of the large M theory, where we let alpha go from 1 to M, with the SU2 theory, which we are really interested in. Okay. And so this is the results for the spin spectral function. Okay, so this is the large M theory, the orange line. This is the theory I've been telling you. I've been telling you about the asymptotic expansion here, how we are very proud to have many different terms here. This is literally the actual answer, the full numerical answer, but it's rescaled to make sure that, well, rescaled to fit the data as best as you can, with the constraint that the integral is the same. So there's only essentially one free parameter in the rescaling. So it's quite, so you would notice here, first of all, if you don't look at very low frequency, there does seem to be the qualitative shape is very similar. But at low frequency, there is a peak. And so this peak was actually first seen by Arkia and Rosenberg, and Henry has recomputed that. And this means that the SU2 model does have spin glass order. And from the integral under this little peak here, you can estimate that order, and we estimate it's 0.01. That may sound very small, but since this order parameter is the square of the moment, you have to take a square root and a factor of 2 from the fact it's spin a half. So that gives you a 20% of the classical moment. So it's not that large. I mean, the square lattice antiferromagnet has a 60% of the moment, so it's a small moment. But the higher frequency behavior seems to match this critical SY spin liquid quite well. All right, so the incoherent component, this is the part here, seems to be similar to this solvable model that I've described so far. All right, so now, how am I doing in time? I don't have any watch here. 2:44, so I have about 15 minutes left. Is that right, Joshua?
Yes, that's correct.
Okay. All right. So now what we're going to do is dope this system. And idea is to get rid of this peak as you dope it. So we can do it, we just take a TJ model. So previously I was talking about this model here. Now I just had some hopping with the constraint of no double occupancy. And then the hopping you also take to be random numbers. Okay, that's the model that actually was first looked at in this previous paper with Joshi et al. So now we're going to do exactly what I described for the J model. We're going to take some large M limit and solve it. And then we are going to compare with exact diagonalization numerics. All right, so yeah, so here's the model. You have 3 states and things can hop around. So I'll go this very quickly since I don't have that much time. So the way you solve this in the large M limit is very similar to the way you solved the spin model. You do this fractionalization. Now you introduce another boson, which represents the holes where the F was the spin-on, and then you give everything many flavors, and you send n to infinity and then m to infinity, and lo and behold, you get a set of SYK-like equations. It's very similar to the equation we solved earlier, except now there's 2 Green's functions, one for the spin-on, the other for the hole-on, and there's some chemical potentials to worry about. But so this long story short is all of the beautiful techniques that were developed for the SYK model can be applied to understand in some detail the structure of the solutions of these equations. All right, so yeah, so I'll skip all of that. In particular, what you find that this spin-dot-spin correlation function going as 1 over tau is preserved. It's even true in the dope model. And furthermore, the electron Green's function also has a Fermi liquid-like form, which is 1 over tau. So this is, if you looked at this by itself, you say, oh, this is just some Fermi liquid, but it's not, because the spin-spin correlation function in a Fermi liquid decays as 1 over tau squared. And the correct way to understand this kind of critical state of this TJ model is in terms of fractionalization. What's happened is that both the electron and the spins are fractionalized, and it's the product of those fractionalized particles that's giving you these simple exponents. All right, so then what do we think? This is the large M solution. So what is the what is the solution at small m? What do we think is actually going on? This is also could happen at large m if you condense some particles. So we think that we found a spin glass at 0 doping. So when we dope it, we think that it just remains a spin glass for a while with some small density of holes of density p. So the property of a spin glass is that the spin-spin correlation function goes to a constant at long time. That's the glassy memory. And then these holes form some kind of disordered Fermi liquid on top of them. So that's the behavior expected from doping the spin glass that's present without in the insulator. At very large doping, we do expect Fermi liquid behavior where spin-spin correlation decays 1 over tau squared, as I just said. And this large M solution, our hope is that it has something to do with the actual critical point in SU2. Which has these characteristics. And we can compute in using the large M methods all kinds of properties of the spectral function here. And we want to now compare how well do they compare with what actually happens in the physical model, physical random model with SU2 at this quantum critical point between the spin glass and the Fermi liquid. And notice I showed you very early on this paper of the French group who was at Marc-Henri doing NMR, which is showing exactly that type of behavior. There's a spin glass order in the pseudo gap, and then eventually it disappeared, and you got a Fermi liquid. Okay. But before I get there, there's another very beautiful property that emerges from the study of this state. You can compute its resistivity. Now you might say, what do you mean by resistivity of a random cluster? Nothing goes anywhere. Well, what I mean here is the resistivity of a slightly different model where you take this high dimension limit, which has essentially the same equation. So you can, the DMFT people have really worked out very carefully how you can compute resistivity by that approach. So if you follow that, you can try to compute the resistivity here. And amazingly, so I'll show you how that works. So this was the spin-on correlation function I've already showed you. This is the first correction from the time reparameterization mode, which is linear in frequency and linear in 1 over tau. And then you can get the electron Green's function, also has a similar form, but now there's no square root here. And then finally from that, you can compute the resistivity. And lo and behold, you get a resistivity that's linear in temperature. So it's this time reparameterization mode, which gave you the first correction to the spin susceptibility with the scaling dimension h equals 2. And as you saw in all the cases, the first correction went as a power of some energy times h minus 1. So in this case, h is 2, h minus 1 is 1. Energy is, the scale is just temperature, and resistivity is linear in temperature. So this is a very robust property of all of these models, because once you have the time reparameterization symmetry, it gives you a linear NT resistivity. And even the correction here, the C rho, is a pure number that we can compute, where gamma is the coefficient of specific heat per site per spin. Okay, there's just one fly in the ointment. If you actually do this for the TJ model, not the J model, you find that there are some operators seem to be always in the large M limit anyway, operators between 1, H is between 1 and 2. And so this would give you an even smaller power, but they come at very tiny coefficients. And there's no reason to suspect that those operators don't have large corrections when you do the 1 over M expansion. On the other hand, this operator that gives you, is protected. So we have every reason to believe if you have such a fixed point in the SU2 model, it will have the same dimension. It'll always be 1. And H will always be 2, and the power will be 1. All right. So that's as far as we have gotten to the challenge I had at the beginning of my talk. How do you get linear resistivity? Well, here's something that almost does it, except for this annoying extra operator that we found and we described in a paper that should be out soon. All right, so now the other question, now let's compare to numerics. So I'm going to show you a bunch of results from, this is actually almost all, yeah. So all the work, the numerical work is the work of Henry Shackleton, and the numerical work is by Maria and Grisha from this large M equations. So this was what I showed you earlier. This was the spin glass peak. So the purple line is the exact diagonalization result. The orange line is the large M theory. Okay, this is the insulator. So now we dope it. Now doping changes the large M prediction slightly, but not very much. And we can only dope tiny amounts in large M. This is some artifact of the large M limit. So you can ignore the green line or purple line. They look pretty much the same. It's very small corrections. So now you see that the spin glass order seems to be going down. And yeah, it goes down and down and down. And around 1/3 doping, it seems to be pretty much gone. And then the fit to this large M solution of this critical point is excellent. But I don't know, it's good. It's actually, but I should say, like as a point, the fact that this is linear and omega over here is entirely a consequence of the time reparameterization mode. The same thing that gave you linear resistivity is giving you this linear and omega dependence here. So that we expect to be very robust. And, it's not a bad fit to what's going on here. And then once you keep going, then, then it becomes more Fermi liquid-like at higher doping from the numerics. Here's another way of showing the plots. On the same plot, this is how this spin glass peak disappears as you increase the doping. And it becomes more and more SYK-like in the spectral function. All right, I think, so there's some other things that we did. Now, some of you may know another property of this SYK critical point. If I take this phase diagram here, if this is really some kind of critical point or phase in between, it has a finite zero temperature entropy. So the entropy of this critical state is expected to be much larger than the entropy of these two states. So one of the things we did in numerics for SU2 is just to compute the entropy of this random model. And these are some of the results. And you can see that there is a maximum in the entropy, around 0.3, around roughly the same point where the spin glass order seems to disappear. We still haven't fully analyzed the data. You can try to even extrapolate to zero temperature, and there's some indication that you might even get zero temperature entropy, but I don't think we have enough data to claim that. All right, so I'll just skip that. All right, so let me just, let me just conclude by just recalling all the results and also some previous work in the context of a more general model, where we just take what's called the TJU model. No constraints here. You have just the Hubbard model with random hopping, and you add some extra random exchange. So you can try to imagine that you have a phase diagram as a function of 1 over u and p. So everything I've told you about is at u equals 0. On the other hand, along this axis, which is u equals infinity. At u equals 0, you would expect some disordered Fermi liquid behavior at all dopings. Now, if you sit at half filling and you increase the value of u, you expect a metal insulator transition. And the insulator should have spin glass order. That's what we have studied, I've described in this talk. And so you expect some metal insulator transition. And there was a very nice work by Cha et al., where they actually studied this by a different method than the ones that described here. They do quantum Monte Carlo on the self-consistent equations of this model. So it's basically a DMFT plus type of calculation using quantum Monte Carlo. And in this paper, at this point, they indeed found this protected exponent of 1 over tau. This is the fit to that. And they also get a linear anti-resistivity. And so our claim is that, that there really is the critical point they found probably smoothly connected in some way to the critical point we have been studying. We've been studying this model here and talking about the physics of what happens here. And that's where you naturally get and robustly get a linear resistivity modulo some caveats that I've talked about, and also spin spectral functions that are not too far off from what are seen in experiments. Of course, everything with a pinch of salt, because this is not a realistic model. It's the model right up here. Everything random and coupled to everything else. But it's amazing how much this very simple model gets. Okay. All right. So that's the summary. So we propose that there's some kind of critical or almost critical state near optimal doping, which is captured even in the random TJ model. And this can be understood in terms of fractionalization of the electron into holons and spin-ons. And this fractionalized model is described by this complicated 0 plus 1 dimensional SR2R invariant conformal field theory, whose most important property is the time reparameterization mode. The new novel property that we haven't seen before in other critical theories. It's, none of the boundary conformal field theories of multi-channel Kondo have this analogous mode. And this gives you, with no fudging, but with a coefficient that, I wouldn't go ahead and fit the data. I don't think so, because there's also a fairly large residual resistivity in the model we've studied, which is linear in T. But we can only study this in the large M limit, and hopefully we'll understand better on how to do the small M cases as we go on. And there's also going to be further work, so I told you about the Shah et al. Work here using the DMFT method. There's going to be another paper describing what happens here using DMFT methods, and that also so far it seems it's all very consistent with the picture I'm drawing here. Okay, thank you very much. Yeah, that's a busy slide, but okay, it summarizes all the things I've talked about.
Okay. So if anybody has any questions, they can either raise their hand or they can just unmute themselves. Maybe I'll start because I had a little question. So this might be somewhat naive, but how does the time reparameterization mode affect the superconductor instability in, say, an SYK model?
That's an excellent question. We haven't studied that. I mean, it's a correction. It's a small, it's a correction to the leading behavior. There have been many papers, people talking about instabilities of non-Fermi liquids to superconductivity by adding in some average exchange interaction, not a zero mean. There's a paper by Avishkar Patel and Nuna came on that. And then you get superconductivity with but where value of delta over TC is now very different from the BCS value. In fact, much larger. So, yeah, I don't. I suppose the time reparameterization mode will change some of that a little bit. I mean, it gives you the subdominant corrections. For some quantities, why was I interested in this subdominant term? For some quantities, like the local spin susceptibility, like I showed you here, this was the local spin, whoops. All these plots were of the local spin susceptibility. For those quantities, the time reparameterization mode is very important because the leading term is just a constant. If you look at the leading term here, here, the leading term here is just a 1. It's just a constant. I mean, it's still it's a discontinuous spectral function at 0 temperature. I mean, but that's so then this leading term is easy to pull out, which is kind of what we've been doing. And the same with the resistivity. For the resistivity, the leading term is just a constant. It's just some residual resistivity rho 0. So to get any temperature dependence at all, we have to include the time reparameterization mode. Now for the kind of thing you're asking, it may be just a correction that we're not so interested in. But there's turned out quite surprisingly to be some quantities for which this correction is everything. And I guess I briefly mentioned, so there's a holographic representation of this in terms of AES2 black holes. Mm-hmm. I was mentioned in the last slide, which Jan Zanen pioneered studying non-Fermi liquids using those AES2 black holes. And what this time reparameterization mode is a graviton on the boundary of the black hole. So it's a quantum fluctuation correction to the leading ADS-CFT answer. Yeah.
So just a follow-up question to that. Is the graviton massive?
Well, this is curved space. No, it has power law correlations anyway on the boundary. It has scaling dimension h equals 2, so its correlation decay is 1 over tau to the 4th.
Okay.
But because you're in gravity in one space and one time dimension doesn't really have a graviton. But if you put it on a boundary, they can be things on a boundary, and that's what this thing is.
Okay. Okay. Professor Hooley, you have a question?
Yeah, thank you very much. So yeah, lovely talk. I was the mismatch between the spin-spin correlations and the electron-electron correlations made me think a bit of two-lifetime behavior in the normal state. Is there any connection there? Can you compute magnetotransport?
Well, that would be hard. Yeah, in these, there's no natural way to extend it and have a magnetic field. I mean, there is a model that Avishkar Patel looked at where you take a lattice model of SYKs with random couplings and you can do magnetotransport there. Yeah, but I would say in our case, the mismatch is, the way I would say is that what that mismatch indicates is fractionalization. So then if you accept fractionalization, then you have to write down a theory for spin-ons and hole-ons, and then there'll be 2 separate relaxation times for those excitations. I mean, in that sense, there'll be 2 times, which is in the spirit of, I think, what Phil Anderson was also saying.
Right. Thanks.
Sure.
Okay. Any other questions?
Yeah, I just have a quick one. Sorry, so I'm coming from the quantum computing side of things. My condensed matter physics is very weak, but one paper that has stood out to me, I think over a year and a half ago, was from D-Wave, where they were able to simulate KT transitions and observe KT transitions on their system, which I found fascinating because it was one of the first proofs to me that their machine was even able to do anything quantum in the first place, like real quantum information, due to the fact that they could actually model the transversizing field. Like that actually kicked in. At least that's what how I understand it. So that being said, when it comes
but
to
the KT, I might correct you a little bit, but go ahead.
Please do. Sure.
It's a finite. It's mostly thermal fluctuations. The KT transition. It's not really quantum. It's not a quantum transition at all. I mean, you need quantum mechanics to define the fact that you have a qubit, but everybody agrees you have a qubit.
Yeah.
The question is there any quantum coherence required between different qubits to have a KT transition? And the answer is no.
Got it. Okay, so that's great, because that was going to be my next question. What do you think is worth sort of trying to tackle with a quantum computer? Let's forget near term, the nuances of whether we can solve it or not. What do you think is the most likely question that we should?
I would say would be to actually study quantum phase transitions. I think D-Wave is trying to do that. I mean, you could also have a 0 temperature quantum phase transition, for that model. I've forgotten exactly that model, but I think, that's, in fact, fully frustrated Ising model that I studied, and it has a XY phase transition at 0 temperature. But I think at this point, they find that their devices are too noisy for them to approach that. There's also a very nice recent paper by Claudia Chamon and collaborators on using the D-Wave machine to simulate Ising gauge theory. And Ising gauge theory in 2 dimensions also has a quantum transition between a confinement and a deconfined phase, where the deconfined phase has some topological order. And that would be a great thing if some of these quantum computers could then, do a quantum simulation of these states with topological order, because they then have topologically protected qubits. I don't think anyone's close to that yet, at least from the style of the superconducting qubits. But there are many other efforts, and let's see. I may be a bit of a skeptic on quantum computing per se, but the devices that people are building are pretty amazing, and I think they will end up studying some interesting quantum phase transitions in the near future. And in fact, for the Rydberg atoms that I've been involved with Misha Lukin's group, in 1D, they already have studied some and seen actual quantum transitions with exponents, and okay, and I'm sure there'll be more results soon. Yeah.
Okay.
Hi, Subir. I have a hi, Subir. I'm Giovanni Vignale. Thank you for the nice talk. I have one question about this. So a natural model that gives naturally the Planckian lifetime is, of course, something like graphene, a system with two, electrons and holes, zero chemical.
Yeah, no, if I could just interject, there's no problem getting Planckian lifetimes in Green's functions or dynamical properties.
Right.
The problem is getting a Planckian lifetime in the resistivity. Go on, sorry, I should have interrupted. Go on.
All right. So you're saying that in the case of graphene, the resistivity would not be linear in T?
It's been a while since I thought about this, but that's correct. I mean, you need disorder or you need some kind of, if you take the quantum critical theory of graphene with Coulomb interaction, and you, for example, looked at the electron Green's function, well, then up to some logarithm, it does have a Planckian width. So there's no problem in getting imaginary part of Green's function that have some Planckian time in them. The trouble is that the resistivity is a special property which is constrained by momentum conservation. So in fact, if you take that same theory that gave you the Planckian time, that has no impurities, it has perfect translation invariance, and the resistivity is, in fact, there it's a constant, because if you have particle-hole symmetry, the resistivity is a constant. So it's either some constant of order e squared over h, or it's zero in the limit that gives you the Planckian time on the other observable. The difficult part is figuring how do you get a model where the resistivity gives you has the Planckian behavior in it. So curiously, resistivity is the easiest thing to measure in experiment, but it's really the hardest thing to understand in theory. And so this model that I presented, the fact that it's effectively in high dimensions or very random, it's kind of important to have that feature, because everything becomes, you don't have any issues with momentum conservation or Umklapp. You don't have to worry about such things. It's just the resistivity is whatever it is, and it can be just given by, you can just determine it by straightforward scaling expansion.
Yeah. So what I was suggesting is that perhaps some of these models could be somehow shown to be equivalent in some renormalization group sense or so to models in which you have the temperature as effectively the only scale, because there is no chemical potential, right? And provide a natural explanation for this. But I guess you're telling me that it's not so simple, right? So okay.
I would say Planckian behavior in many observables is not, has been understood and quite well, I think, but the resistivity is the difficulty, is what I would say, and other transport properties, also.
A very quick technical point, so at some point in discussing the solution of the first model you discussed in detail, I was under the impression that you introduced at some point an approximation that I omega is negligible compared to sigma of omega, right? So
that was to obtain, yes, go on.
Yeah. So is this an approximation that is, so have you gotten the general solutions without this approximation, or do you depend on this approximation for your results?
The answer is the first, yes, we don't make that approximation.
Okay.
So if you make this approximation and you drop this term, you can see my screen, right?
Yes.
Then then this solution here, this is the complete solution. This is the full answer. Done.
Okay.
Okay. This is just tangent.
Okay.
So in the limit, you drop the omega. This is the complete answer. Nothing more to do. It's done. This is the full solution.
Right.
So everything else I was telling you. So in this limit, if I plot the Green's function the way I plotted it here, this would be just a constant equal to whatever that number is.
I see.
So I've just taken that squared out. It would just be a constant. So everything here that you see, all of these terms, other than the constant, come from the I omega term. It's all the effect of the I omega term.
Okay, okay, I understand. So you don't have a closed form solution for the general case. You have these asymptotic expansions and so on.
Yes.
Is it right?
No one has a that would be quite impossible.
I mean, that would be nice.
But numerically, it's, you know, you can get an extremely accurate solution. You can say just, yeah.
Thank you very much.
Yeah. Sure, thank you.
Okay, any other questions? Yes, Professor Hooley.
Yeah, if there's time, may I just ask a sort of question of interpretation? So you motivated or you showed us the time reparameterization invariance coming out of this pair of coupled equations for the Green's function and the self-energy. Yeah. But given the important role it's playing, I find myself wondering, is there a way of seeing that that's going to emerge in this kind of model without going through the diagrammatics?
Absolutely, yes. I mean, you can just look at this equation. I mean, the important property of this equation, these equations of this type, and you can also have an action, all right? So what are things that can destroy time reparameterization invariance? Well, if you have any derivatives, they will destroy time reparameterization invariance because, that's why the I omega is like a derivative. So you have to throw that out. But we have good reason for expecting that in any non-Fermi liquid-like solution, the I omega won't matter because you're being taken over by some anomalous self-energy. Self-energy is larger than the bare term. And then if you don't have any derivatives and you don't have any other explicit time-dependent interaction, it's got to be time reparameterization invariance, pretty much. Then you need a saddle point, which is scale invariant, which you will want to have because otherwise, yeah, but that's a separate issue. Yeah, I mean, you don't need this, you know, going from here to here doesn't require any assumption of anything. It's just, you know, these 3/4 and 1/4 simply come from the fact that there's 2 powers of G, 3 powers of G here, and 1 power of sigma here. Sigma and G must have opposite powers or have power to add up to 1, and that's all. I mean, you know, every time you have an integral, you get a derivative, you get an f prime. And so you cancel those f primes that you get from the integral by the f primes and the rescaling factors. That's all. And then everything is, so the integrals, you know, integral over d tau becomes integral of d sigma, and the Jacobian factors cancel with these. I mean, this is exactly what you do in a conformal field theory, really. So as long as there's no explicit derivatives or any explicit time dependence from an environment, you're pretty much guaranteed to get it. It's remarkable how simple this is. I mean, I was when, you know, I struggled so long in trying to understand the structure of the original SY equation in the 90s, and then the moment I saw Kitaev give this argument, I said, "Oh my God, I should have seen this."
Thank you.
Yeah.
Any other questions? So I'll maybe wait 4 seconds.
I mean, the step that he took that I didn't take, which was crucial, just in case you're asking these general questions. For this to work, you have to imagine a more general problem where everything is a function of 2 times. You just say, okay, let's imagine that, which I had also discussed in a separate paper, unfortunately. I didn't see the connection those days. And if everything becomes a function of 2 times, then this transformations is totally obvious. Yeah.
Any other questions? So maybe I'll wait 4 seconds if anyone wants to unmute themselves.
Okay, thank you, everybody.
Okay, thank you. So let's all thank Professor Sachdev one more time. Thank you.
Thanks very much.